Hello, General Biology, and welcome back. We're in Chapter 2. This is Section 2.2, and this is the third screencast in our Section 2.2 series. And we're talking about acids and bases. And this still goes along with the properties of water, where we learned about polarity, cohesion, and adhesion, and how that enabled suspensions and solutions to be formed. And now we're going to talk about the pH. And pH determines whether something is an acid and a base. So about 1 out of every 550 million molecules of water goes through a split. It goes through a breakup. So I'm going to go back and I'm going to draw my, let's try this again without making it look like a Pac-Man. I'm going to go back and I'm going to draw our water molecule, and we have our hydrogen here and our oxygen there, and remember that there's a pair of electrons here, and then there's two other pairs of electrons that are in this area. So what's going to happen is this water molecule is going to split. As I said, 1 out of every 550 million molecules of water goes through this split. And the hydrogen winds up losing an oxygen, and then the oxygen and the other hydrogen stay together, but they wind up keeping all of the electrons. So because this hydrogen loses the electron, it winds up becoming known as a hydrogen ion, and because this oxygen and hydrogen kind of keep that electron, they become known as a hydroxide ion with a negative charge. And we know that in a solution, the number of hydrogen ions that are present in that solution and the number of hydroxide ions that are present in that solution is going to determine the pH of that solution. So water molecules are going to split apart. They're going to form these two ions. So here's the actual chemical equation for that. And notice the arrow is going this way and that way. And that's because these can join back together again to form water as well. And this water splits into that hydrogen ion, we saw by the picture how, and the hydroxide ion that's present. And look, hydroxide ion, that "ide," lets you know that there was a transfer of electrons that took place. So as I said, in pure water, about 1 out of 550 million molecules will split, and they will wind up providing a solution with a number of hydrogen ions and a number of hydroxide ions. When we think of pure water is going to be equal in the number of hydrogen ions and hydroxide ions. So we say that water is neutral. Pure water is going to be neutral because it's going to be equal in those. But there are solutions where the hydrogen ions can be greater or less than the number of hydroxide ions. And this is how we determine whether something is going to be an acid or a base. So let's talk about this. We use something called a pH scale. And the pH scale tells us about the concentration of hydrogen ions that we have in a solution. So the pH scale runs from 0 to 14. A pH of 7 is going to be neutral, where there's going to be an equal number of hydrogen ions and an equal number of hydroxide ions. But when we think about what happens from 0 to 6 and 8 to 14, this is where we look at the changes that take place in those numbers of hydrogen ions and hydroxides. If you are on the scale between 0 to 6, you're going to have more hydrogen ions. And if you're on the scale from 8 to 14, you're going to have more hydroxide ions. Okay? When you have more hydrogen ions, that's an acid. So the more hydrogen ions there are in a solution, the more acidic it is. The more hydroxide ions it has in a solution, the more basic it is going to be. So you're going to have a lot more of that. Now, let's take a look at the scale. And we're going to start over here. When we're at 0, we have the most amount of hydrogen ions. Okay? That's the most amount. So anything at 0, that's going to be a really strong acid because it has the most. As we move closer to 6, we're going to decrease in hydrogen ions. All right, so there's going to be less hydrogen ions. We're still going to have more than we have on this side, but there's going to be less. So this is going to be a weak acid. Okay, but it's still an acid nonetheless. So let's take a look. Stomach acid, that falls between 1 and 2 on the scale, so we'll say 1.5. Since that's close to 0, stomach acid is a strong acid. Let me tell you how strong that is. If you were to take stomach acid out of your stomach and put it onto your car, it would eat in through the finish and into the paint of your car. It's that strong. Okay, so it's really, really strong. When we look at what's a weak acid, rainfall, our natural rainfall, is a weak acid. Milk is a weak acid. Remember, neutral, it's going to be equal in the number of hydrogen ions and the number of hydroxide ions. Okay, so look at what are acids. They're things that are sour to taste. Okay, tomatoes, they have a sour base to them. Okay, bases. Bases, as we said, run from a scale of 8 to 14. So when we look at 8, look at how close 8 is to neutral, and that's where we're going to have an equal amount. So we're going to have less hydroxide ions here, so that means that this is going to be a weak base. And when we get to 14, we're going to have the most hydroxide ions here, so this is going to be a strong base. So the closer you get to 14, the stronger the base is going to be. Look at our cleaning supplies. Oven cleaner, that's 13.5 on the pH scale. That's a real strong base. Bleach is 12.5. Ammonia. And all of these things are kind of bitter. Instead of being sour, they're bitter and they're slippery. And they're cleaning agents that we have. So that's how the pH scale is going to run. Again, solutions with a pH below 7 are called acidic because they have more hydrogen ions than they have hydroxide ions. And the lower the pH, the greater the acidity. So if we get here of a pH of 1 or 0, that's a really strong acid. Solutions with a pH above 7 are called basic because they have more hydroxide ions than they have hydrogen ions. The higher the pH, the more basic the solution. So if we get up within this range, that's a really strong base that we're going to have. So what do you think? What if I took something that had the pH of 12 and I mixed it with something that had the pH of 2? What do you think would happen? Excuse me. Hopefully you're going to say, "Oh, Mrs. Saunders, I know that answer." They're going to even out, and that pH is going to be somewhere around 7. So you can add an acid and a base together, and you can neutralize that. You can help change the pH. Can you think of anything that you might take in order to do that? I'm a little bit ahead of where I want it to be. How about an antacid? Have you ever taken anything like Tums or Pepsid or something like that? What that is this antacid is usually a base. And stomach acid, remember, is 1.5. And because it's a base, it's going to raise that pH level up and neutralize it so that you don't get that acid indigestion and that acid irritation. These are referred to as buffers. Take that back. They're not buffers. Don't call them buffers. I'm wrong. But they're going to neutralize that. Okay, we'll talk about buffers in just a minute. Okay, so each step, let's talk about this, each step on the pH scale as we're looking at this. And I just got unplugged. Hold on one second here. Each step on the pH scale represents a factor of 10. So a liter of a solution with a pH of 4 has 10 times as many hydrogen ions as a liter of a solution with a pH of 5. So these go by tens on there. Acid is any compound that forms hydrogen ions in a solution. So we know stomach acid we were talking about is a very strong acid. Stomach acid is actually called hydrochloric acid. It's one of the strongest acids that are in your stomach that helps with the process of digestion, and it can range anywhere on the scale from a pH of 1 to 3. Bases are a compound that will produce hydroxide ions in a solution, and bases are also referred to as alkaline, and that's what I wanted to say when I started to talk about the antacids. Antacids are alkaline, they're basic. They have lower concentrations of hydrogen ions than pure water. And girls, I asked this on a test, so please make sure that you get this. They have lower concentration of hydrogen ions than pure water, and they have pH values that are above 7. So strong bases like lye that have sodium hydroxide in them that are used for making soap, they tend to have pH values from 11 to 14. So they're very basic, very strong bases on the scale when you get up to 14. Here's buffers, and this is what I started to make the mistake with. Buffers are fluids that are found within the cells that actually help prevent sharp, sudden swings in pH. So one of the ways that organisms control the pH is through compounds that they call buffers. And these tend to be weak acids or weak bases that can react with strong acids or strong bases that prevent sharp, sudden changes in pH. So think, okay, if you were taking a bubble bath, and that bubble bath contained a really basic solution to make the bubbles, the soap, and your skin level is acidic, you wouldn't want a sharp, sudden change with your cells because that would cause them to stop functioning properly. So you have buffers that help regulate that pH so there isn't a sharp, sudden swing that takes place. If you add an acid to an unbuffered solution, it causes the pH of that unbuffered solution to drop. But if you have a buffer in it, it will only cause a slight change in that pH. That's what a buffer is going to do. Alright, that's the end of the screencast in section 2.2. That means that we're going to have a test. The test will be on section 2.1 and 2.2. Alright, have a good one.